Hi, my name is Nicole Ostertag, and today I'm going to be talking to you about LNG-powered locomotives. Many of you may be asking yourself, what is LNG? LNG stands for liquid natural gas, which is natural gas in a liquid form. Natural gas is made mostly of methane and is represented by 4 carbon molecules. When you convert natural gas to its liquid form via liquefaction, you can do this in 2 ways. The first is the cascade method, which essentially cools the gas that in turn was cooled by another gas and continues to be cooled by the previous gas until it has reached a certain temperature. There is also the Lindy method, where the gas is cooled regeneratively as it passes continuously through an orifice until it is cool. Some of the properties of LNG include that its energy density is 2.4 times greater than compressed natural gas, which you may be familiar with as a method for fueling trucks. Its energy density is also comparable to propane or ethanol, and has 60% of the energy density of diesel. LNG fuels locomotives in that it is compressed and over time warms, giving off energy to provide power to the locomotive unit. This presentation will explore why you should use LNG as a replacement fuel for locomotives, replacing diesel as it burns as a much cleaner energy. Increasing government regulations and legislation have proven that the industry is more concerned about carbon emissions and how they can possibly reduce those emissions. Additionally, there has been a recent discovery of a plentiful supply in the United States. As the natural gas infrastructure network continues to grow, it's aided by recent discoveries of new shale deposits, such as the Bakken Shale deposit in the North Dakotas and the Eagle Ford Shale deposit in Texas. Additionally, fracking has become a new technology that has increased the productivity of many wells. By forcing water, chemicals, and sand down into the well, they are able to create additional fractures, obtaining more crude oil and natural gas in the process as a byproduct. As a result of this increased plentiful supply, the price of natural gas has significantly decreased, and this provides potential financial savings for users of diesel fuel. Here's an example of what the natural gas pricing comparison looks like when you're looking at the price of natural gas and how much that costs you to use that product versus how much you would save relative to gasoline. So that first row you'll see is a $4 natural gas price. That's been the typical price for the past year or two. As you can see that provides a cost reduction relative to gasoline of over $1 per energy unit. So who is using LNG today? First, let's look at the history of locomotives. Locomotives originally were fueled by steam engines. Today they're fueled by diesel fuel, and potentially in the future they will be fueled by LNG. However, LNG is not new to the U.S. market. It was first produced here in 1918 and currently has many uses, most predominantly for heating and electricity generation. As you can see on the screenshot of figure 5.2 that I've included in this presentation, the use for electric power has been the most significant increase over the past few decades. This is primarily due to increased legislation that has created incentives for green energy use. So if LNG has all these great properties and advantages, why hasn't it taken off yet in the locomotive industry? The first uncertainty is the natural gas prices. While the prices have remained low for a year or 2 years, they're not necessarily going to stay that way. Additionally, there are high capital costs to switching to LNG. Let's take a look at Union Pacific, one of the 4 Class 1 railroads in the United States. Union Pacific has 8,000 locomotives in their fleet. Presuming that the cost of producing a locomotive powered by LNG remains the same as the cost of producing a locomotive powered by diesel fuel, that cost is $2.5 million for each locomotive. When you take that times their 8,000 locomotive fleet, that represents a total investment of over $20 billion. Additionally, many of the locomotives will have to have cryogenic containers behind the locomotive containing additional LNG to fuel the locomotive. This is because LNG has a lower energy density than diesel fuel and will take up more space to provide the same amount of fuel and mileage. Each one of these cryogenic containers costs roughly $200,000 each. Presuming that half of the fleet, or 4,000 locomotives, will need one of these cryogenic containers, that creates a total investment of over $800 million just for Union Pacific alone. Additionally, all of the railroads have very expansive networks with thousands of track miles across the U.S. Looking again at Union Pacific as an example, they have over 32,000 miles of track and cover 23 states. That will require multiple LNG fueling stations across their network. Each one of these LNG fueling stations is estimated at $4 million each, also a substantial capital cost. Since this project is in the early stage, I've classified it as a technology trigger phase step within the Gartner hype cycle. There have been several tests completed over short distances only and involving only 3 of the major 6 railroads that go into North America. There are no workable or reproducible models, and while some testing has gained publicity, there has not been a large following for this project. Additionally, due to the financial challenges we just discussed, the commercial viability of this project is unknown. So what's next? In the next 5 years, I see there being continued testing on locomotives. People are definitely interested in this technology, and they're interested to see how we can make this affordable for companies to convert to this technology. I do see that there will be continued increased regulations and consequent implementation for trucks. Trucks have, on average, much shorter distances that they cover, smaller fuel requirements, and a lower cost of capital, making the truck industry much less cost prohibitive than the rail industry. Over the next 10 years, I expect that short-line railroads, those are railroads that are regionally based and cover much smaller territories than the Class 1 railroads I mentioned before. I see these short-line railroads adopting due to some of the same advantages we just discussed of their trucking counterparts. From there, I continue to see progressive testing on locomotives for the Class 1 railroads as well, with hopefully a possibility to convert to this technology in the future.